Hello, my name is Wan Amar and we are from Group 7. We're presenting our case study. Here's are the table of content of what we will be presenting today. Now, let's look at the introduction. Distillation column is the most widely used method to separate liquid mixture into its component fraction based on the difference of volatilities. There are several components that make up the distillation column. The first one is vertical vessel, where separation takes place. Vessel internal helps improve the separation by utilizing the trays or packing. Condenser to condense the top products. Reboiler to vaporize the bottom product. Reflux drum is to retain liquid from the condensed vapor to be recycled back into the column. Now we look at the design consideration. Design consideration are basically what are the consideration made for the design of the column. The consideration can be divided into four, which are the first one is the number of stages and the reflux ratio that can be calculated using Mercalli-Thiele's or Franke equation. Next, there are also consideration on the sizing of the column, which is we look at the height and also the diameter of the column. The third one would be the column internal, where the trays or packing are being using in the distillation column, and what type of tray will be using, as well as the hydraulic design. The last one will be the design of the column, where we look at the design temperature, design pressure, material of construction, design loads, corrosion allowance, as well as wall of thickness. Next, I will pass to Alia to present the design procedures.
Next, we'll process design where the mass management will be conducted to determine the molar flow rate of this plate and bottom, and proceed to KIDO antibubbles by using trial and error but to satisfy these equations. And by having these assumptions, the Mercalli-Thiele method can be used for the distillation column designing, and R min can be determined by utilizing this equation to know the pinch point, and it can be referred in figure 1. Then we'll proceed with theoretical trace by constructing ROL, Q9, SOL, and it can be referred in figure 2, and then proceed with real trace by assuming every trace having the same efficiency, and lastly for physical properties by assuming the constant molar ratio, the top and bottom for liquid and vapor molar flow rate can be determined. And these are the figures as mentioned before. And these are the summaries of the process design calculations. And then we proceed with physical column design, where the column height will require a safety factor for the stages, as in this case it is taken for 10% corridor reference, and initially the trace spacing is taken over 0.5, and proceed to column diameter, where the flooding velocity needs to be calculated, and by taking 85 of it for design vapor velocity, the column diameter can be calculated and taken for the highest, as in this case the bottom, by having 1.2 meter. And these are the figures and summary for the physical column design. Then we proceed to plate hydraulic design, where the liquid flow rating will be determined by using this equation, and from there you can see that a cross flow with single pass will be taken, and then proceed for provisional plate design, where by referring to the reference, these particulars can be calculated for the provisional plate design. And then to avoid whipping from occur, whipping checking need to be calculated by determining the minimum vapor velocity at the whip point. And these figures are used for the calculations in the previous slide. And these are a part of summary on plate hydraulic designs. Next, we proceed with plate pressure drop, where by having these ratios from the values calculated in previous slide, the orifice coefficient can be determined from figure 5. From there, the total across the plate can be determined. And next, we proceed with gun carbon liquid backup, where it is being calculated to determine whether the estimation on the trace spacing made in the previous slides are acceptable or not by referring to these inequalities. Next, the perforated area can be calculated by taking the assumption from Sino and Thaler for typical cases, and the number of holes can be determined by using this equation. And these are the figures and summary calculated for plate hydraulic design. Next, I'll pass to Doris for utilities and mechanical designs.
Thank you, Alia. For utilities requirement, we have calculated for condenser and reboiler. In terms of cooling requirement, we have calculated the heat removed from the condenser and the amount of cooling water required. In terms of heating requirement, we have calculated the heat transferred to the reboiler and the amount of heating steam required. And the values are as stated. There are two assumptions made, where the reference temperature is equal to the feed temperature and the enthalpy is constant throughout the temperature development. Next is the mechanical design. For material of construction, we have selected carbon steel since it is cheap, low corrosion, easy to weld and high strength. The design pressure is 1.1146 bar with 10% of safety margin. The design temperature is 100.79 degrees Celsius with 50 Fahrenheit of safety margin. For welded joint efficiency, we have selected double welded butt joint. The minimum wall thickness is 0.0025 meter, where we assume the column diameter equals to the internal diameter. For head enclosures, we have selected torus spherical shape since the operating pressure is less than 10 bar and it is also suitable for liquid vapor phase system. For design load, we have calculated the weight of shell and also the wind load. For vessel support, we have selected skirt support since the distillation column is tall and also vertical vessel. Next, I'll pass it to Ming Han for safety consideration.
I am Ming Han and I will be presenting the safety consideration. There are a few standard codes to be followed when designing the unit operation. For example, when designing the piping sizing, ASME 36.1 and ASME 36.19 will be required, whereas the maximum allowable stress for material of construction like carbon steel, stainless steel, and others will be found in ASME BPVC Section 2 Part D. Lastly, ASME BPVC at Division 1 could allow to design, manufacture, and certify the pressure vessel. Next, I will talk about the safety consideration of chemical involved. Distillation column is one of the unit operation that is reactive and decomposition hazard, and product of distillation column might have high volatility and flammability. Hence, improper storage and handling can lead to chemical degradation and potential hazard. Safety consideration need to be considered like property, storage, and handling and hazard of chemicals used when designing the distillation column. By doing so, safety of all parties can be guaranteed. For benzene, it is a colorless liquid and its boiling point is 80.1 degrees Celsius. It is advised to store at fireproof place in a tightly closed container and handle empty containers with care. The hazard of benzene include being flammable liquid and vapor, and chances of skin and eye irritation. For the aspect of toluene, it is a colorless and flammable liquid, and its boiling point is 110.6 degrees Celsius. It should be kept away from direct sunlight or any sources of heat and stored at a place with ambient temperature in a closed container. Handling of toluene include working under local ventilation, handling unclean empty containers, and no waste discharge. The hazard of toluene include chances of skin irritation and drowsiness. Next, I will pass to Xuan for the cost estimation.
Thank you, Steve. Now I'll talk about the cost estimation of distillation column. For cost estimation, these are the assumptions made. And for distillation column, it is a vertical pressure vessel with safe tray. All the cost calculations are based on Appendix A of the reference book by Turton 2012. First, we have to calculate the tower bare module cost using the formula given. To do that, we have to determine the volume of the vessel, which is approximately at 15 meter cube. Based on the figure shown at the right side, it shows that we required a purchase equipment cost of the pressure vessel at $800 per meter cube. Next, pressure factor will be determined, and using the values given in the reference book, the base case purchase equipment cost of the pressure vessel will be obtained around $2,700 per meter cube. And based on the SEPC given in 2021, around $77,000 will be obtained for the tower bare module cost. Next, to determine the sieve tray bare module cost, the formula given is used. And from the formula given, we have to determine the FQ value, which is determined at 1 for number of trays more than 20, which in our case is 23 trays. To use this formula, we have to determine the tray area, which is approximately at 1.1310 meters squared. And based on our figure at the right side of the slide, it shows that we need a purchase cost of tray at around $940 per meter squared. In base case, we can obtain the sieve tray bare module cost at around $22,000 per meter squared, while in 2021, the sieve tray bare module cost is obtained at around $46,000. So all in all, we can obtain a total bare module cost at around RM 515,000. Next, I will pass to Steve for a conclusion.
In conclusion, this case study has shown that distillation is an essential process for the separation of mixture of benzene and toluene. The same procedure for physical column, plate hydraulic design, and mechanical design for distillation column are carefully considered for efficient and smooth operation. Lastly, safety consideration and cost estimation are carried out on the design distillation column to ensure the safety and profitability of the equipment. That's all from our group. Thank you.